Welcome everyone. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. And today's application-focused webinar will be taking a look at measuring thermal conductivity in geological materials and thermal grouts. So jumping right into it, wanted to just put a little message out there, really who this webinar is for. Looking at different areas of applications that would be relevant to geothermal scientists, engineers, looking to measure real geological samples. So whether you're at a geothermal R&D or lab team, looking at some of the cores or some of the materials that are actually coming out from the subsurface, alternatively, the grout and material developers that are working to formulate and benchmark performance for grouts that are being used as conductive backfills. Or maybe you're in an adjacent subsurface discipline, enhanced oil recovery, geothermal mapping, mining and exploration, anywhere where thermal conductivity plays a role. This is essentially what we're going to be looking at here today. So before we go into the deep portions of today's session, really wanted to highlight that, when we're looking at this area of application, the measurement becomes really important, and it's compounded by a few different factors. One of the big challenges we see is the high throughput testing requirements. Some of these geological projects, you're getting hundreds of core samples, and you need to be able to efficiently test those without, of course, sacrificing your consistency, your repeatability, and accuracy. Another big one is the representative conditions. These are things we're going to be talking about. What you're measuring in the lab should be representative of what's actually going on in the environment or in the system in question. So we're going to talk about some of those factors. And then lastly, the other big one is the sample format versatility. So being able to test not only the solid cores, the cuttings, maybe we're looking again at the geothermal grouts or the slurries. These varying formats all dictate different methods that are best suited to address those. So these will be some of the themes that we're talking about here today. So before we get too far into it, just want a little introduction to who we are for folks that may be new. So C-Therm Technologies, we're a world leader in thermal conductivity instrumentation, specifically focusing on non-destructive, transient-based approaches, working with researchers, manufacturers, and quality control professionals across varying industries. So of course, this will be our main focus in today's webinar is around the thermal conductivity characterization. Wanted to start out with just a little bit of a testimonial here. Thought this would be quite relevant for kind of the talk here today. So this one I picked kind of notes, Trident has been a helpful toolbox for a lab at the Geological Survey of Estonia. We were able to test various rock samples and are very happy with the device. So always good to hear that. That was from Heikki Boert from the Geological Survey of Estonia there. If you'd like to see some other testimonials or what other folks have to say about their experience working with us at C-Therm, again, feel free to scan that QR code and take a look at some of those comments on our website. So for today's agenda, wanted to break it down. Here we're going to start out with a bit of an introduction to the application space. We're going to kind of, again, go into some of those challenges that I had mentioned at the beginning, diving into them in a little bit more detail. We'll take a look at C-Therm's Trident instrument and give some explanation on what those options are. And then we're going to go into some data. So we have some different application examples that we've collected, take a look at some of the published work of clients of ours that have used the instrument. And like I said, at the end, we will tie things up with a Q&A. So starting with our introduction, really, looking at, the reason behind why thermal data is important in these types of geothermal projects and what's going on in this space. So essentially, just kind of looking at the image here, as you can imagine, in any type of subsurface system, you're looking at a geothermal loop, there's a lot going on. It's not just one singular, let's say, material or interface. We are dealing with heat exchange between, the ground, the formation, through different materials like the grout, the fluids that are going into these systems as well. And whenever we're looking at heat exchange, of course, thermal conductivity becomes crucial. That's, if conductivity isn't well understood, it's going to introduce ceilings and bottlenecks. And of course, this can compound in issues. This could result in oversizing the loops that are being generated, which, is going to be a form of waste. Or on the opposite end, undersizing. And then you're going to have performance issues as well as challenges over the lifetime span of these systems that are developed. So, some of these loops here, you saw some pictures like this is some of the grout that's placed, that geothermal grout in some of those systems. Again, the big thing that we'll take a look at is, how are we actually measuring these? So a lot of these cores are removed for testing, not just for thermal conductivity, but thermal conductivity being one of the important aspects here in terms of performance that we'll be taking a closer look at here today. Speaking of the cores, we're going to go over some data with these. For folks that may be, again, new to this space or just kind of getting some info on this, these core samples come out in various formats. I was doing some investigation here, and depending on which type of drill site is used, kind of the size and the overall structure there, we can actually get varying sizes of cores produced. Some of these are noted to be, the NQ size, about 47 millimeters in diameter, up to PQ, which can be 85 millimeters. So there's varying sizes involved here. And why that matters in the context of thermal testing is that oftentimes the geometry of your method can be a constraint, or the samples have to fit a specific requirement here. On top of that, like I said, thermal conductivity is going to be the focus here today, but there are also other tests that are often done on these samples as well. So ideally, not having a destructive measurement or the preparation to measure can also be quite important there to retain and save those materials for either repeat testing or, again, testing with other properties. So the cores will be certainly something we'll take a look at here today on how to best measure those. But as I said, the other side of things are maybe looking at some of those thermal grouts or geothermal grouts. So these are interesting materials because, if you think of a traditional, like a grout that you might use in your home renovations, these are not that. They may have some similar components, or you could say maybe some analogous characterization, but these are often cementitious or bentonite-based slurries, often with very high quality thermal additives within the system, because again, the focus here is not only kind of having that structural component, but it's a very key factor in the heat transfer within these systems. So your grout is essentially acting as a bridge here between that fluid and the formation. So again, looking at where bottlenecks can come up, the thermal transfer between those two areas is something that really needs to be quantified and understood in order to optimize some of these systems. You can see here, like I said, there's typically binders, additives, some of the conductive fillers that you'll see could be graphite based, also very high quality, silica-based sands as well. There's a variety of different formulations and chemistries that can be investigated, but ultimately here, where thermal is a critical attribute, that has to not only carry those desired mechanical properties, but the thermal aspects as well. So a little bit of a background there. But like I said, there's some big challenges in this space, and there's three main ones that we'll take a look at here today. And talk about the relevancy for them. Are they, major challenges? Or are they just kind of, let's say, more annoyances? But in the context of the three that we picked here, these seem to be ones that have popped up time and time again with the groups that we've helped work or supported for their work in this space. So challenge number one, throughput. Like I said, there are often hundreds of samples that can be produced from some of these projects. Maybe if you're on the grout formulation side, or maybe you're verifying formulations of dozens of these different grout systems. And ultimately, your project timelines are highly dependent on your lab's turnaround time. Many of these projects, depending on the planning, they have short turnaround windows. to iterate on material performance and improvements, you have to do this in a way that allows for fast feedback. The long traditional approaches to measurement, which would be like your steady state systems, can really bottleneck the workflow here, which is why we're going to be taking a look at where transient can come in to really support this. This image here, you can see this was a Utah core facility. This entire building exists just to store these core samples. Our CEO, Adam Harris, actually showed me a video the other day of a tour that he did on a facility over in Europe. And similar, you walk through and there's just massive amounts of these core samples. So you can imagine, depending on what's going to be going on and or how many of these need to be tested, you have to have some ability for throughput capabilities there. So this will be something we'll address. The other one is the representative testing conditions. For folks that are familiar in this space, you'll be well aware that once, if you take something out of its, natural environment, which may be, meters or kilometers down, what you could be testing in the lab might not really be representative of what that environment is. Whether you're looking at the different, the pressures, the saturation levels, or the temperatures that exist down there, you want to really make sure you're doing an apples to apples comparison, because if you test, let's say, just ambient room temperature and you call that, representative of your sample, that's where you're going to get some, potentially significant mismatches in what the actual thermal performance is going to be. So yeah, temperature, pressure, saturation, these are three areas that can all impact your measurements. I'll make a note that, many of our transient solutions have testing across a broad temperature range. We'll actually share some data coming up where we look at the influence of a saturated core sample. And unique, we do offer pressurized thermal conductivity here at C-Therm. So taking your samples, putting them under confined, pressurized environments. These are all things we have supported in the past and would be happy to discuss if that would be relevant to your research needs. And like I said, the last one here that we'll take a look at is just the variety of samples. Again, how you go about testing something like a core here versus maybe you're looking at an aggregate or a soil or a non-compacted material versus something that's more like, almost liquid, like grout, slurry-based material. The big issues that we see with groups is taking what might be a really good method, but trying to broadly apply it to every single sample and testing condition that they run across. This is really where you can run into some issues with method mismatch. So again, with Trident, we'll take a look at how the different methods can come into play for these different scenarios to really best address the specific task at hand. And the last thing I wanted to mention here is kind of some of the industry standards that we see referenced in this space. ASTM D5334, this is a standard in reference to the TLS, or transient line source. Covers, within the standard, there's a lot of information that you could take a look at, but loose, soft, unconsolidated materials. We've also seen this applied for testing of solid samples. You just have to drill into it to, meet that TLS requirement. But certainly one that is quite often referenced in the geological space. The other one over here, the ISO 22007-2 for the traditional transient plane source, or TPS. This is an output for the measurement of thermal conductivity and diffusivity. Really great for testing like those rigid solid materials, your core samples, maybe some of the cured grouting materials you might come across as well. So in terms of like industry specific standards that we see coming up, or groups that are looking to do their testing in conformity to, I would say these are two of the more popular ones. So, we're gonna take a little pause here for a second. My colleague Carter is actually we're gonna do a quick poll here. Folks, you should see something popping up on your screen there. If you wouldn't mind, we'll take maybe 20 seconds, 20, 30 seconds, just to address like what is your biggest challenge in geological thermal conductivity testing? If you're in this space, are you also encountering some of these issues? Are there other challenges that we didn't list here? Please feel free to let us know. All right, seeing quite a few responses come in. Thank you everyone for the participation here. We'll share the results here shortly. Maybe give it another 5 or so seconds. Right. So let me try this. So this should, let's see, hopefully show up on screen here. Share results. There we go. Yeah. So kind of looking at what folks are saying, interestingly, the representative testing conditions, that seems to be accounting for almost 50% of what folks are struggling with. I can imagine, yeah, getting the data, like we said, the thermal, the temperature, saturation pressure, these are certainly some of the big factors that can be challenging, but very important to address because, again, your effective thermal conductivity can be highly influenced by those. Okay, interesting. And for the folks that put other there, if you wouldn't mind sending a message to us directly, kind of saying like, what are their challenges? We could see if we could certainly be able to help you guys address those. But all right, I'll stop sharing that. Thank you, everyone. All right, we'll move forward. Okay, so I think this is a great time to, of course, introduce C-Therm's Trident instrument. It's one instrument with 4 methods for thermal conductivity. So our different methods that we'll be taking a look at here today, MTPS, the TPS and TLS, which I touched on for the standard side of things. Also, the hot wire won't be featured as heavily in today's content, but if you are dealing with liquids, heat transfer fluids, immersive cooling technologies in your work, this could also be one to keep an eye out for. But again, if you had any general questions, feel free to shoot those along as well. So this quote here is one that we really like to use. It really embodies the idea behind Trident. When all you have is a hammer, everything looks like a nail. And kind of what I was talking about there earlier, when you take a method that might be really good at what it does, but when you try to, let's say, apply it to a solid core, the grout materials, a soil, there can be some mismatches or some challenges there. So with Trident, again, you really have more of a toolbox style approach to really tackle the jobs that those methods are designed to handle efficiently. For those of you that are joining, maybe you're newer to the thermal conductivity space, or folks that have, you've been in the industry for a while, but you just kind of want some different literature, like information to read. We have recently published, it was towards the end of last year, an updated method selection guide for thermal conductivity. This goes over not only the Trident methods that are available on the system, but other methods that exist in industry, steady state options, even some of the optical frequency and time-based techniques. So if you're looking to get some insight into what that method landscape looks like out there, where they're most commonly applied, definitely I'd highly recommend taking a look at this. Again, it's a free resource. You can download that using the QR code or find it on our website. And for those folks that are maybe looking to learn a little bit more, about Trident, or if you maybe wanted to speak with us one-on-one, maybe get some budgetary information, there are two codes you can take a look at here. The quotes are free, so you can scan that. You can put in your information. We'll be able to give you some costing structures for the Trident system. This code here will send you directly to a booking link where you can get some time with someone from our team and one of our subject matter experts to walk you through what the options are, learn a little bit more about your application, and maybe we have, of course, more of a discussion around what what you're essentially going to be required, and help find a solution that really fits the research and the testing that you're looking to do. So again, definitely feel free to take a look at those there. And also, if you've missed any of these links, send us a message, and Carter, who's moderating, can send you those links directly. Okay, so this brings us to some of the application data. So these first few examples, this is some internal data that we've collected, looking at some of the rock cores as well as the geothermal grout samples. So the first one here, looking at TPS, the transient plane source method, testing a dry and a saturated sample. Just a little bit of background on the TPS. So as I mentioned, it conforms to the ISO standard. It's a double-sided sensor, which is placed in between two sample halves or two pieces of the material. Your measurement times for a TPS, we're talking seconds to minutes in time scale. So nice option there for relatively quick testing, vastly superior compared to, again, the more steady state options. And specifically for cores, why we are looking at the TPS here, this is a non-destructive method. In this case, we wanted to test the same sample in the saturated state and also in the dry state. So we obviously want to retain the same material for that testing. So non-destructive. And the sample size requirements for TPS align well with even just the kind of your default core sizes that come out for testing in the lab. That even being said, we do have flexibility on our TPS sensor sizes, so there are varying options available. So maybe if you were dealing with somewhat of an irregular material, we can certainly have a discussion around what options would exist to address those. So kind of looking at some of the data here, essentially it was interesting because there was two different samples. There was a sandstone material and a shale. We first tested them both in the saturated state. This was actually, these samples were provided to us by a local company here, which had a specialized pressurization and saturating system there. And essentially what we did, we took the samples both and 100% saturation. You can see between the two, there was, a fairly notable difference in terms of conductivity between the sandstone and the shale, which may not be that surprising. But where we see some very interesting results is that when we go to the dry state and the differences in between those individual samples. So the sandstone here showing a notable decrease, about 22% different compared to that saturated state. Whereas the shale, not so much. There's more, I think maybe 2%, if that. So a very minimal change was observed there. But again, how this has bearing on your design is that if you are, again, maybe making an assumption about the material, testing it in that dry state when actually it is partially saturated or fully saturated, just that alone can result in, almost a 25% shift in performance. So again, understanding the implications of those real world testing conditions are going to be really important. The next one here is looking at some of the grout materials. So here we opted for the TLS. This is one we've worked with some groups that have specifically doing their testing around the ASTM D5334 standard. This is a great option for these types of samples. The probe is inserted directly into that mix. You do not need a rigid sample geometry like again, slurries, non-solids. There's actually applications not related to this webinar here today, but for like polymer melts, for other applications. The TLS is certainly a great option there. And it's completely encased in stainless steel, so it's nice and robust to deal with some of these material types. The same sample or the same method here could also be applied to the soils, to those aggregate cuttings as well. So very versatile, especially for the geological material applications. So what we actually did here, we took a neat grout matrix, measured that just at room temperature ambient conditions. But then we actually kind of formulated an example here where we added a 10% by weight conductive filler into the mix. I mixed that all up and then retested that sample. And we showed just doing something very simple like this, we saw about an 18% shift in the thermal conductivity. When you look at thermal conductivity of many like commercial grade thermal grouts, these can be in excess of 1.5 or even 2.5 watts per meter Kelvin. Again, where you may have some of those very specialized binders and additives. But, from this example here, it really just illustrates the point that, fillers are a big part of what are driving the performance. Again, the other constituent parts also play a role, but, when you're looking at conductive fillers being, their own separate, I'll call it ingredient in the recipe, what type of filler you choose, how much of it you're adding, these can directly impact that heat exchanging performance that is observed. So, those are just a couple little examples that we've collected here. Thought would be quite relevant to share with you all. I wanted to end today's webinar with an example of some published work by groups in the industry that are actually using the Trident system, specifically here, actually the MTPS method. And we're looking at an example that was done over in Europe on geothermal design. So the title of the paper that I'm referencing here is an updated ground thermal properties database for GSHP applications. This was taken on by G. Santa and all. This was published in 2020, but a really, really interesting paper. It was part of the EU Cheap GSHP's project. There were 17 partners, testing done with collaboration over 9 countries, and hundreds of measurements were taken to complete the work in this paper. Kind of some of the backing or the reason behind the requirement here, the desire for these folks to do this is, again, kind of developing a reference database. This is an excerpt from the paper where they actually noted that depending on where you look, the reference values for some of these, what may be viewed as common materials, can vary widely. Like just this was some data on some sands and some silts clay samples, but again, the same essentially material, but varying thermal conductivity values depending on the source. So to really help, address some of this variation and kind of come up with a consensus around values, the team here that was doing this testing, again, performed hundreds of measurements on rock samples, unconsolidated sediments, using C-Therm's MTPS to baseline their performance. So I'm showing here some of the data again from the paper that was published. These are on some of the solid samples as well as some the sedimentary, igneous, and metamorphic rocks. You can see the colored data represents the MTPS results compared to where you can see those wider bars, sometimes referencing quite a wide range of performance here. But really what this did is these measurements on these multiple samples provided an expanded essentially recommendation for the values to use, where in scenarios where the literature values were just too wide ranging. So MTPS being one of the fastest methods on Trident, it helped to address the literature versus lab discrepancy, but also part of the reason why this was so uniquely qualified for this application is the high throughput capabilities. Your MTPS test times, like I said, amongst one of the fastest on the Trident. You're looking at average delivery of heat pulses for about 1 to 3 seconds in duration. So, to screen through hundreds of samples in this regard, having that speed, not really a nice to have, it is essentially a requirement. All right, so wrapping things up, we're going to end with one last poll here before we close things out here today. So Carter, if you don't mind popping that into the chat. Awesome. Yeah, just looking to get some information from you guys. Like, what field or industry are you guys coming from? I know we focused, a lot of this on maybe some of the geothermal side of things, but I know there's a wide variety of applications where, geological materials are being tested. So yeah, if you have a moment, just let us know a little bit about where you guys are coming from. Awesome. Seeing some answers come through there. We'll let this go for maybe another 5 or 10 seconds or so. All right. Thank you, everyone. So share these results here. So yeah, no, interesting. I mean, I'm glad a lot of you folks are coming from geothermal. Hopefully this information sparks some interest or is relevant there. A lot of academic researchers as well. So yeah, always happy to see our academic groups joining in these types of sessions. And yeah, a few other areas as well, and some non-geological folks. So awesome. Thank you so much for that. We'll stop sharing there. All right. And yeah, just the last few minutes here, just going to kind of close things out here today. So if you are looking to get some more information from us, maybe like dive into some of the resources, again, feel free to take a look at some of these QR codes. Our testing services offered by thermal analysis labs. We offer more than just thermal conductivity, full thermal characterization, ranging in thermal conductivity methods, but also, thermal analysis and calorimetry, DSC, DTA, TGA, etc. And it was good to see some academic support, academic groups joining here, because if you don't already have a system and you'd be interested in getting one, we do have quite a nice academic support program in place for that. So again, feel free to kind of take advantage of these QR codes or shoot us a message for the link. I'd also just like to make reference to our partnership with ZFW for their line of TIM testers and high temperature heat flow meters. If maybe you have colleagues that are dealing with other material types, or maybe there's also some application of these in your research. We do support not just the transient methods on Trident, but with ZFW, we are now able to offer some really, really high quality instrumentation for TIM testing and some unique capabilities on the high temperature heat flow meter. So hopefully this sparks some interest with you folks. Again, nothing that makes me happier than joining on some of these demo calls, walking you through a technical consultation, showing you how the instrument works. Definitely feel free to book some time with us there. And the team is always standing by. If you are looking to get some budgetary information, please feel free to take advantage of that. You can, of course, use these codes on screen or visit our website, ctherm.com. You'll be able to find all the different information on the varying applications as well as these resources there. So please feel free to take advantage of that. And at this point, we're on the way to wrap things up. I would just like to say before we close things out, if you are looking to stay connected with us, up to date on everything that we're doing, LinkedIn is where we post all the latest and greatest content, upcoming webinars, application resources, blog posts, also the conferences that we'll be attending. Everything gets posted there first. So give us a follow if you're not already doing so. And also kind of plugging our YouTube channel here. We've recently really gone into doing a lot more video content. So I've gotten comments from some folks already that, they're getting a lot of good information from those. So if you're looking for educational, application focused video content, easy to digest, gives you information that's relevant to thermal conductivity and the other thermal properties we work with, feel free to check that out. All right, so for the folks that are dropping off at this point, I would just like to say thank you once again for joining our webinar here today. I'll go ahead and close out the formal recording at this point. For those that are interested in sticking around, please feel free to do so. We will be going into the Q&A next. Thank you, everyone.